Welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and in this video I wanted to have a look at sub-Neptunian planets and then the sudden radius cliff in this particular group of planets. There's a sudden drop off of the number of planets at a particular radius and why that might be the case. So firstly, there's lots of different sorts of planets that we have. So you've got hot Jupiters, cold gas giants, ocean worlds, rocky planets, all those sorts of ones. But the ones we're really interested in for this particular video are ones that sit around here. These are your sub-Neptunian planets. So here you've got the orbital period of planets and then the size in Earth radiuses on the y-axis, and they can exist kind of anywhere really, any orbital period, so close to the star, further away from the star. But sub-Neptunian planets basically are between the size of Earth and Neptune, hence the name sub-Neptunian planets. So they are mass-wise at least between 1 Earth mass and 1 Neptune mass. That's about 17 times the mass of Earth. So that's typically where their masses sit. And most of those will have a radius somewhere between that of Earth and that of Neptune, which is about 4 times the radius of Neptune. Now I say most because actually you can still have a sub-Neptunian planet that has a radius that is larger than Neptune. Those actually will be classified as like a super-puff planet because they're quite low mass, but they're also quite large in size. And there's a different video on that one really explaining what they are, and actually very rare, but most of them have a radius less than Neptune. And in another video, I had a look at the actual distribution of those sub-Neptunian planets, and you get basically a radius valley essentially. You get two distinct groups. It's a bimodal distribution between 1 Earth radius and 4 Earth radiuses. You get a super Earth group and then like a sub-Neptunian group, which is like the larger one, and there's a dip in the middle, and we explain why that's the case. It's mostly because they lose their atmospheres and they kind of transition into the other one. But the thing we're interested in for this particular video is this radius cliff. So once you get to a certain size, there's a very sudden drop off in the number of planets at that radius, at that sub-Neptunian sort of size. And it occurs around about 3 to 3.5 times Earth radius. There's a very, very dramatic drop and lack of planets at that particular size. So why might that be the case? Well, let's have a look at sub-Neptunians and kind of what they're made of essentially. So it's assumed that they have these rocky cores, and they also have quite a large atmosphere as well. So if they were to lose their atmosphere, they would actually be terrestrial planets. So their rocky cores are not necessarily much bigger than a terrestrial planet, but the big difference is this outer atmosphere, which is very large. So it also has quite a lot of hydrogen in it. So think of your gas giants. They are predominantly hydrogen and helium. This is true for sub-Neptunians, but they don't have quite as much hydrogen, but they still have a lot amount of hydrogen in their atmospheres. And the core, whilst it's a rocky core, it's likely going to be very hot because during the formation process, it will heat up the core. And if these are still quite young, it's likely going to be magma and basically liquid, essentially. So it's going to be like a magma ocean there, surrounded by this hydrogen-rich atmosphere. So interestingly, at around about 2 to 3 times the radius of Earth, when they've got a sufficient atmosphere around these kind of magma ocean cores, it's actually sufficient enough to force the hydrogen into the magma ocean. So it kind of dissolves into the magma oceans. And this occurs around about 2 to 3 times the radius of Earth. And if you think about it, it's kind of the same way in which we make our fizzy drinks. So we actually dissolve carbon dioxide into water at pressure. You increase the pressure, you can basically dissolve it into the water. Same sort of thing that's happening here in a way, just it's hydrogen and it's then essentially very, very hot rock, it's magma. So you're just dissolving that hydrogen into the magma instead. Now, what happens then as the planet continues to grow, because this might be actually in the formation process, because actually this is what's going to limit our size essentially. As the mass increases of the planet, the atmosphere gets bigger, then the pressure increases. That then actually forces more hydrogen into the magma. So you get more hydrogen dissolving into magma as that pressure increases and it grows even more. And this actually stalls the planet because that hydrogen is then dissolving into the core, and it stalls its growth at that point because that hydrogen's been lost into the magma, essentially. So around about this size, the planet's growth begins to stall. Now, at some point, that magma will become saturated with hydrogen. You can't get any more in it, no more can dissolve, and then the planet will start to grow again. So at some point, that will happen. Now, most planets actually don't make that saturation point. You need to get to quite a significant size to basically overshoot that and then continue to grow. So what happens is these planets, they start to grow, they then stall, and if they actually are able to get big enough, they then they go past that saturation point and they continue to grow again. And most planets actually don't make it that big. So planets with enough gas to reach beyond this saturation point are actually rarer, hence you get that radius cliff. So there's less planets that can go beyond that saturation point, and again, that's what causes our kind of lack of planets at that point. Most planets stall there, and that's it. That's where they will then remain. So thank you for watching, and if you enjoy, then check out some of the other videos.